Awesome. Cool. Well, thank you guys all for coming. I know most of you have traveled a pretty long way to be here, so super excited to see what gets built in the next couple of days. At a high level, this workshop will be going through what is LayerZero, how can you get started building on it, what is the full stack of things that you can create using the tech, and going through a little bit more in detail some code to get you guys started. So without further ado, my name's Matt. I'm a developer ecosystem lead on our DevRel team at LayerZero Labs. You can follow me at Uncrackable on Twitter. Feel free to ping me at any point during the weekend if you guys have any issues that you run into or need support. I'll be online for most of it. I always start off these presentations with the physical world representation of a bridge because I think it's important. Most of us have seen a bridge, but we probably don't think that deeply about what is a bridge doing at a high level. Obviously, it's connecting groups of people on different places, right? But more than just the people that's being connected, it's the information that they hold. Having a bridge, at least in historical times, was incredibly valuable because it meant that you could then coordinate the transfer of goods and services. And with the transfer of goods and services came the financialization of those services. So bridges, in general, are very, very useful for moving information and value. With cross-chain, it's no different. If we look at the blockchain industry today, developers and users are constantly facing trade-offs depending on what chain you want to go to, whether it's an L1 or an L2, depending about the finality on that chain and the time it takes for a transaction to be included in the block, the cost of the block space itself. Each of these things make you as a developer face different realities about what you can and cannot build on each blockchain. At a high level, if we talk about maybe the most common use case for blockchains today, the movement of value, right? This is a simple ERC20 contract on Linea. At a high level, when we think about moving assets, right, from point A to point B, we like to think of it as an actual movement, but really all we're doing is updating the ledger state. We're saying, I want to deduct an amount of balance from one user and then credit that balance to a destination. But as soon as you move to a cross-chain environment, that immediately becomes a lot more complicated. Each of these chains are isolated. They don't have any context about the other network. And so as a developer, we need to think about a way for us to call some sort of transfer function, know that the assets in question have been debited for sure, and then somehow relay that message over to the destination network and instruct it to call some function that receives those tokens for the intended user. So this is the domain space that we're working with, especially when it comes to value transfer. But if you're just working on that kind of value transfer level, you need to also ensure that this cannot be abused, right? If we just allow anyone to make that receive call without good confirmation that this is a valid function call from a source blockchain, you can easily wreck the network and wreck the protocol. In general, the way that we solve this over time was with the concept of monolithic bridge security. You can think about this in the center here as some centralized provider that's listening to events on a source chain and writing them directly on a destination. You could think about this as a collection of different verifiers. You could think about this as a middle chain where the central verification schema is just a middle chain bridge. But in general, there would be some entity in the middle that you relied on and you basically put all of your trust in to ensure that they were going to be able to verify and deliver the messages on your behalf. But again, we have this problem here where if that is such an easy solution to the cross-chain space, why are so few people building on more than one chain right now? This is from the Electric Capital Developer Report. And these numbers have been going up. More and more people are becoming familiar with cross-chain development. But the major problem, I think, right now is that we don't often think about what happens when these security guarantees fail or backfire. As soon as your security goes down, not only are you, the single application, at risk, but every application on that network is simultaneously at risk that uses the protocol in the middle. This could be due to a number of things, whether it's just a flat-out centralized service moving messages between chains. This could be due to the client software used to secure each of the validators that sign off on a message if that client software has a backdoor, or it could just be due flat-out to a lack of node diversity, which is how the Axie Infinity Bridge hack happened. So in general, the main problem is that once a messaging protocol fails for bridges, every application that touches that messaging protocol fails as well. And this has been a stark reality that we've seen in the last probably decade for blockchain development, where the majority of hacks and exploits we see that have the largest value attack are due to this centralized or monolithic bridge security. So in my eyes, the way I like to frame it is, if you think of Ethereum as a dark forest, cross-chain is a dark ocean. You have each of these islands that don't know about each other, and the only way for you to get knowledge from one chain to another is to rely on some actor to control that message and pass it through to the destination. And if a malicious actor controls the port of entry for that island, the island itself faces an existential threat. Simultaneously, if a centralized entity accidentally destroys the port via some upgrade to the contract or the interface itself, the island also faces an existential threat from not being able to get reliable information to the chain. So the way that we see LayerZero is addressing these two issues. The one of, if the protocol fails, every application fails, and two, the destruction of the actual interface that developers use because of the upgradability of the contract interface. LayerZero is a permissionless protocol, meaning that LayerZero, the entity that owns the endpoint contracts, cannot block or whitelist or blacklist anyone from using the contracts themselves. The endpoint interface is fully immutable and permissionless for anyone to use. And furthermore, it's censorship resistant in that once a message is emitted from a source blockchain, an arbitrary user or arbitrary actor can't strike that message down without invalidating the protocol guarantees. And finally, as I mentioned before, it's immutable. This people go over quite a bit, but I think it's more beneficial to probably see it in code. From the protocol stack for just majority of message passing on bridges, the way that message passing works is that there is at a low level an omnichain messaging layer. The way that this layer works is that it is focused mainly on the verification of messages from point A to point B. This is that collection of different signers, the testers, the middle chain bridge, whatever it may be. LayerZero allows the application to select the block confirmations. You have to wait on a source chain, the required verifiers in the stack, the optional verifiers as part of that stack, and the threshold needed for a message to be considered verified. We'll dive in a little bit more into what that actually looks like. On top of this low-level layer for verification, we need a way to actually route function calls. So this omnichain function call layer operates on top of the message verifications and allows the app owner to control the amount of gas limit, message value, order of execution, and the executor to use for each call. We have two different call methods that you can use. The LZ receive execution, which is just part of the LayerZero receiver interface. This is for receiving any message packets on a destination chain, and LayerZero composer. We'll dive in a little bit deeper too into that as well. And finally, the most important bit for the application developer, what you guys will be hacking on, this app standard layer. So applications on top of these two other parts of the stack will essentially use these different functions to enable different use cases within different EVM environments. We have an OAP contract standard that lets you move arbitrary bytes between point A and point B. We have an OFT, Omnichain Fungible Token standard for moving ERC20 token balances, and an ONFT standard, which lets you move NFT transfers between chains. At a high level, this is the send workflow. An application, whenever they want to use LayerZero, will create a call on the LayerZero endpoint called endpoint.send. This call allows you to specify a message in bytes that you want to deliver to the destination chain. You will specify the destination chain identifier as an endpoint ID, and you will provide a send configuration of what off-chain stack you want to use to deliver that message on your behalf for you. As part of that configuration, you can decide the amount of block confirmations that must be waited on the source chain before this off-chain stack gets started, and you can assign the job to specific verifiers and an executor of your choice. Today, LayerZero has 30 plus different verifiers to choose from, and as part of this security guarantee, you're able to choose the required number of verifiers. So in this case, let's say we ping 4 different decentralized verifier networks about this message in particular. 3 out of 4 of them have to sign off on the message's integrity, and this is enforced by the application from what they set on the destination chain. Again, it matches your send config, so in the send workflow, we say wait this many confirmations, the receive config enforces it. It also enforces the expected DVNs that are meant to sign off on the message and that threshold for security. Once the message has been verified, you can simply have an executor, whether that's a user calling the endpoint directly or a automated executor that LayerZero runs, automatically deliver the message on their behalf with an automated gas abstraction for them. So this is a high level at the workflow. You initiate a send transaction, it emits to some off-chain entities based on your configuration. Your receiving app enforces that it matches the configuration you expect, and then finally you execute that message through to the destination chain. So this kind of builds into us what we think of as this omni-chain application, the idea that any smart contract on any chain just has to interact with a single LayerZero endpoint that is already deployed on that network and can be routed to any other blockchain network within the stack. Furthermore, we are able to configure things a little bit more deeply. Each application has a concept of this bytes message, right? So in general, if you're used to ABI encoding bytes on Solidity, the way that it works is just ABI encode any data type that you want to deliver to the destination chain. From there, when you have the receiving call being made to the destination app, you will decode that message and extract the bytes inputs with ABI decode. For the OFT standard, there's a message codec library called messagecodec.sol that I recommend you guys look into. It'll give you a bit more advanced usage for how to splice bytes out if you're interested. And finally, within the app, there's a final little piece of application layer security. Each application sets a peer address for that pathway. So you can see here on the send side, we select this destination endpoint that we want to deliver to. And what this security, this peer is doing is I'm saying within my application, from this endpoint ID, I want to ensure that this is the address that's sending the message. So it enforces once again that you have the verifiers that are checking the integrity of the actual message itself, and you know that the origin is coming from the place you expect to prevent any invariance. Again, same thing works on the send side. We check the peer and we just say get peer or revert for that destination to ensure that you have configured a correct peer on both chains. Going a little bit deeper into the tech stack, the way that the LayerZero endpoint actually works is that it's an immutable smart contract interface. And what I mean is LayerZero, once this endpoint is deployed, cannot arbitrarily change configurations to rug your application. The way that your application interacts with the endpoint is that you will use it for both the send and receiving function calls, but you'll also use it to set your configuration. Once an app has set a selection of decentralized verifier networks by an array of their addresses and set the executor by its address, there's nothing LayerZero can do from our end to change it. So entirely permissionless and entirely owned by the application. Underneath the endpoint, we have a secondary contract called a message library. You might be wondering, why is there a LayerZero V2 if I haven't heard of LayerZero V1? LayerZero V1, without getting too into it, was a separate collection of smart contracts that enabled you to instead choose an oracle and a relayer. When we decided to create endpoint V2, we thought, well, we want to bring some of the benefits of this configurable security stack and separate execution logic to the existing apps that were already built. And so we added these appendable smart contracts, these message libraries. What this allowed you to do is, as an application, you could call this function and change which library I was using for my application, enabled you to upgrade from this Oracle relayer setup to a collection of security from these different DVN providers and executor. And so it was a guarantee for developers that they still had an upgrade path to the latest and greatest security without using upgradable contracts, just appendable configurations that the application owner set. Nothing forces a user to use this configuration once it's set. It is purely optional and something that they are able to configure at their choice. Going a little bit deeper, we have this idea of DVNs, right? What are DVNs? Well, in general, when we talk about DVNs, it can technically be anything. Most bridges have some method for essentially listening to the source chain, learning about the state, and writing that state to the destination. And so as an application, this provides you a way to not only future-proof your app by, if a latest and greatest verification schema comes out that moves messages cheaper, faster, and more securely, you can add it to your security stack. But it means that you as the app owner aren't forced to accept a one-size-fits-all model for security for cross-chain messaging. You're able to easily configure any number and type of verification within your app and be able to ensure that If something better comes out that beats all of them on price, your application isn't stuck and forced to redeploy contracts or completely change the infrastructure underneath. So with all that in mind, taking a more kind of stepped back approach to token transfers, the way that LayerZero does it is pretty straightforward. You'll deploy an OFT contract on each chain you want to connect, in this case, Linea and Ethereum. And when a user interacts with that OFT contract, all it's doing is calling a debit method, which interacts with the underlying ERC20 token interface to burn those tokens on a source chain, route that message from the LayerZero endpoint, given the OFT's unique security stack that they've configured, and then once it's executed, credit those tokens to a destination address for the amount listed. And what that means is, going back to our previous example, if one of these verifier networks outright fails, your application at worst is simply paused until you reconfigure a new security network and your threshold, or at best is completely uninterrupted, right? If this is a 2 out of 3 security setup, your application has not been halted at all, and it gives you a future-proof path to avoid any issues at the verification layer, which is ultimately the most important. Outside of that, LayerZero lets you configure a lot of other settings that we talked about. For example, the block confirmations, the message execution for whether it's automatic, where a user only pays in a source gas token and it'll automatically be swapped for the destination native gas that you need. Or if a user wants to make that call manually, they can do that as well. Deeper on those execution gas settings, we have specifically the amount of gas limit and message value for the receive call, a composable call, which I'll dive into in the code example, and strict nonce ordering if you want to enforce that messages have to be delivered in a specific order. I recommend checking out the docs or coming to the booth afterward if you want a deeper dive into kind of what these configure options mean. But finally, I think the thing we care about mainly is what this all builds up to. The Omnichain tech stack for us is a way for any application use case, whether it's DeFi, SocialFi, gaming, Oracle feeds, identity, to be built in a way where they can control the not only type of security that they're using, the type of execution logic that they hold, and ensure that they're interacting with a common interface across every single chain. You don't have to learn a completely new chain interface or application interface to unlock new security. Instead, you can have a simple, immutable interface that you've always used for your application and easily configure new types of security within your existing apps. So I'm going to jump past these really quick because I'm short on time. If you want to scan this QR code, it'll be the repo that I start going through in the next 1 to 2 minutes. The last 10 minutes of this talk will just be going through an example design pattern repo to kind of show you what is the design space that LayerZero has, and hopefully the demo code doesn't break, but we should be good to go. Awesome. So switching over here, let's just take a look at this repo. Before I dive in, let me show you how you guys will actually get started building on LayerZero. If you want to use our CLI tool, which I highly recommend, the way you'll start is you'll run npx create LZOApp at latest. This will ask you a couple questions. First, what do you want to call your project? I'm going to call this new LZOApp, and it'll have you choose a selection between an OFT template or an OAP template. In this case, I will choose OFT. It'll also ask for what package manager. I'm going to use Yarn because I like Yarn, and then install some dependencies. For me, it's going to complain about Node because I forgot to switch it, so make sure you're using Node version 18. And if you run into any issues like that, all you need to do is cd into the application, run Yarn, and it will pull down all the dependencies that you need. Fortunately, though, I have another package that I've already set up, so we don't have to realize that. And one of the things that I think is most helpful about this repo setup is that inside, it's a hybrid repo that contains both hard hat and Foundry. So you can use common hard hat tasks that you're familiar with. You can do common Foundry testing. And I'm going to go through 3 contracts. First, at a high level, how do I deploy my OFT? This is a strictly vanilla OFT. The only change I've made is I've added this mint function to mint 100 tokens to the message sender. Within this repo, what's really cool is we kind of expected you guys to start doing a lot of these deployments out of the box. So you can run, it's still going to complain about Node, which I'm going to cancel. I'm just going to switch here to make sure we're set. Perfect. So I'll run LZ deploy. What it'll do is it'll automatically compile your hard hat artifacts, pull them in, and it's going to read from your hard hat config. In this case, I've already set it up to include my Sepolia endpoint, my Arbitrum Sepolia endpoint. This is just a handy package that comes standard with the repo to let you pull down what the endpoint identifiers are. From here, I'll hit, oh, don't want to hit enter there. I want to hit enter in the terminal. It'll ask what deploy scripts I want to use. In this case, I'm just going to use my MyOFT deploy scripts. Hit continue. Public RPCs will do their thing. Great, I've just deployed 2 contract addresses on Arbitrum Sepolia and 1 on Sepolia. Now, once this is set, I ideally want to be able to actually configure them to work together. So I'm going to use another handy configuration called npx hardhat lz oap config init. With this, I'm going to pass in the location that I want my configuration to be. In this case, I'll do it as example LayerZero config.ts. And I'm also going to pass it a contract name. In this case, I'm going to pass it MyOFT. That's the contract I'm working with. And this will, again, ask me to select what networks I want to populate it for. And it will generate this file in my working directory. It will pop out here in just a moment. Awesome. So what does this actually give us? If we format this document, we can see it sets up for us first an instance of the contract on each chain as an object itself, Arbitrum Sepolia, Sepolia contract, tells us the endpoint we're working with. And then it will automatically bring in the default configurations for this pathway. Default configurations, you can be thought of it as like placeholders that LayerZero has set for you just to get tested and quickly started. These can be changed though with all of the addresses available in our docs if you go and look at the deployed contracts page. In this case, the ones that we care about are how do we make sure we can send a message from Arbitrum Sepolia and then receive it on Sepolia. I'm actually going to comment this part out just so you can see. So we have a send config and we have a receive config. The way you can think about it is that in this top part of the repo, for Arbitrum Sepolia to Sepolia, I'm just specifying a send configuration that will call some functions on Arbitrum Sepolia as the from contract. It'll set what my required DVN is, the block confirmations I need to wait, and then similarly for the Sepolia contract, it will provide its receive configuration. The important thing is that this receive configuration matches this send configuration, right? So from Arbitrum to Sepolia, we're sending. From Sepolia to Arbitrum Sepolia, we're receiving. Awesome. From there, I can run npx lz oap wire, pass in the oap config that I have provided, example.layerzero.config.ts. Don't want to update Slack right now. And from there, we can just see it go through, and it will provide me with a little preview of the transactions about to sign. Oh, it's already wired because I've done this deployment once. Great. If you haven't done this deployment, it will basically output and check what that looks like from your end, but we are good to go. In that case, I'm just going to do a simple send transfer. So I've included a simple task in this repo to send tokens. You can see how this task works. It just takes in an amount I want to send, in this case 1 token, to my destination Sepolia, to this wallet address from this network, Arbitrum Sepolia. From here, I can hit send. Public RPCs will do their thing. We'll send 1 token to the network, and then we'll get this send transaction initiated with a LayerZero scan link. So I'm going to open this up. We can see here that once it's indexed on the source chain, it'll immediately populate in LayerZero scan. You can see the messages in flight. The cargo is 1 mock OFT from this address, and you can see it went to the burn address here. You can see which applications are in it, what gas is being used on the destination chain, and we can wait for this message to be delivered. I don't want to waste any time, so while that's being delivered, let's see if we can jump back over here. Perfect. I have 3 other example contracts in this repo that aren't basic OFTs. These are some more advanced design patterns that you guys can implement. The first one is an ABA type call. So this is for you to send a transaction that returns an acknowledgement back to the original sender. The way this contract works at a high level is that we basically will take in a couple parameters when we do this send function. We'll take in the destination that we're sending to. in this case, a string message, and some gas settings that I've specified. I have the ability to add, on top of some required gas settings, some optional ones that I'm having the developer use. So I would play around with this in the repo when you get a chance. From there, we initialize a send call. It will emit message sent. And then on the receive side, decode that message, check if the message type is this return acknowledgement, and return a secondary send call back to the original sender, which you can see here. We're using this origin struct provided as part of the receive call here. So returning back to the sender a message, in this case, a predefined one that I've said, chain B says goodbye. So I don't have this one deployed. Instead, what I'm going to do is actually take advantage of the Foundry test helper that we've built. We have a special test helper contract that you can use in your Foundry unit tests to kind of mock LayerZero implementations within Foundry Forge. In this case, we want to do test ABA, and we're going to crank the verbosity on this one. It's going to compile, hopefully pretty quick.
Hello.
Awesome. Oh, yeah, are we on time? Oh, okay. Isn't it 30 minutes?
5 minutes.
Oh, 5 minutes. Gotcha. Awesome. I'm going to try and speed run this. But yeah, you can see here if you run the same command in this repo, we can see for the ABA contract on chain B, when we call this data field, and let's just pull up that test so we can make sure that I'm not lying. We can see here in test ABA that the assertion is basically checking for the chain B data, that it says chain A says hello. And we can see that it's asserting for chain A sender that it says chain B says goodbye. So we know that their messages were received on destination and acknowledged. I don't think I have time to go through the other two, unfortunately, but if you want, please come by the booth. I will show you myself. One of them is batch sending, so being able to, in one send call, essentially do a for loop that sends to multiple different destination chains if you wanted to mass update data on other chains for one call. And the other call or other contract that we have is a simple composed example that shows you basically how after I receive some tokens from my OFT transfer, I could have a external function call here which executes after the receive logic. But I think for now, I'm just going to pause and open up the questions. Threw a lot at you guys. Thank you guys for the patience. Cool. Any questions? Let's speed run them. Yeah.
Is it propagated already, the first test you did?
Yes. Which test? This one?
The first message.
Oh, yeah. Let's take a look. Yep. Delivered. So we can go on destination, check here. And the way to check and make sure it's delivered, you can check the decoded input data, see that this is the source endpoint ID it came from, what nonce it is, the message, and then in the logs here, we care about the actual value being transferred. You can see a OFT received event emitted here with amount received. Yes?
For the presentation, is it possible to transfer native token like in here, directly with the LayerZero?
So there's a way to transfer native tokens. You can see in this gas setting here, within this call, this LZ received gas, this is 65,000 Wei of the native gas token on Sepolia, so ETH on Sepolia. We allow you, for the executor, to specify message value in gas in the native gas token up to a native gas cap. So if you want to do large transfers of native gas, you're going to need something else, but this is how you would do it in the calls. Yeah. Any other questions or, yep?
What size would you use the OFT versus OAP?
The difference?
Yeah, and like.
So that's a good question. Exactly, yeah. So if we look at the OFT contract, if you go in the stack here and go into OFT core is an OAP. OAP is just a standard contract interface that brings in all of the basic configuration logic and things you might need in your interface.
So if you wanted like I'm trying to do like cross-chain swaps, so I'd use like an OFT contract then because it's swappable.
Yep, exactly. You could do it for ERC20 tokens, or if you had a different token standard, you would just modify on top of OAP. Yeah. Cool. Yes.
Last one, is there a maximum gas limit when you transfer data or OFT?
On destination chain, there is a max gas limit. Yes, it's It varies per pathway, but you can read it on chain. Yeah.
We can do complex operation, decorating contracts using LayerZero.
Yes. Yeah. Cool. Yes, you can. Yeah. Yeah, and if you need more gas than what's provided by LayerZero, you can use Stargate, which is a native bridge, and just use their interface to get even more native gas assets via the bridge itself.
But there is no cap set by LayerZero to...
There's a cap set by LayerZero for the execution options. I can explain it a little bit more too. And then Stargate has no cap. It's whatever you pay for, you get. Yeah. Yeah. Cool. Yeah, thanks guys.